Number 5, can we have timelines on the next milestone events? Not very accurate, but at least know how they will happen one after another. With regards to timelines, the first public timelines that we're going to be announcing around this is going to be just prior to the ERC20 release. Reason being is that the further away you are from sort of a delivery, the more uncertain it is, and the closer it is, the more certain you are. So far internally, we've been consistently ahead of schedule on the delivery of the technology. Drop 1 finished, drop 2 in progress. We expect to have drop 2 done before we list, which I can give you that much information. Drop 3 and drop 4 are in some ways the higher risk ones from a timeline point of view. So drop 1 and 2 are the highest risk ones from a technology delivery point of view, especially around the consensus theory. So things like first getting consensus working, getting the mempool working, getting basic client functionality, and doing some basic low-level system testing around consensus. That was all done in drop 1. That's the sort of the most, like, you might have some unknown unknowns in there in terms of theory. That was all completed successfully. Drop 2, another theory milestone around proof of stake, so the Sybil protection being implemented. And then drop 3 and drop 4 is essentially just making sure that there's no bugs, making sure that the system is secure, making sure that no one's going to lose money on the network. And it's sort of around drop 3, I'd say, that you end up getting some potential issues that were sort of unknowns around the edge cases of the network. This is what happened to us with regard to the previous version Tempo. The reason that we're much more sure about that not happening this time around is because of how we've separated out the technology drops. So the consensus roadmap, the second link that I've put into this chat, essentially lays out how the difference between the shard, how we go from an unsharded to a sharded model, and how we go from a single event linear system to a parallelized system. So the basics of it are already in place in RPN1, but a lot of the sort of more difficult consensus implementation stuff, so where we're really starting to push the boat out in terms of what's been done before, that's sort of pushed down the road to RPN2 and RPN3, which allows us to test in a much more staged manner the technology. Can you compare RPN1, RPN2 and RPN3 in terms of development work required and technical risk? Sure. So in very simple terms, RPN1 doesn't have any shards in place. So you don't have to worry about the state transfer function between shards. And basically what this means is that you don't have this need to stitch together multiple consensus nodes working on different consensus objects and make sure that those all work in a synchronous fashion across multiple asynchronous shards. There's a number of risks that come in around this, around things like validator selection in a multi-sharded environment, where the validator selection essentially has to happen by agreement between the subnodes, the nodes on those subshards, rather than everything happening on in the same sort of shared state. So that sort of change in state view is the hardest part, which doesn't really come into RPN3. RPN1, no sharding, single event consensus. So like essentially is blocks. It looks very much like a blockchain. The first block of transactions come in, all nodes see that block. It's picked up by agreement by the leader. That's then broadcast around all of the nodes who are involved in consensus, which is basically all of the nodes that are allowed to be that are staking over a certain amount on the network, which is limited to 100 nodes, or at least 100 nodes in the first version of RPN1. And then the next event is then tagged onto the previous event, which is essentially, again, a block of transactions. So far, so normal. However, what you'll see in the pictures that are on the GitHub repo in the second link I sent, you can see that the state information is still split up as if there was shards. So the particles already have a mapping in them, which means that they can be sharded at a later date. So when our RPN2 comes along, you're now doing consensus in parallel. So you can have nodes working on multiple non-conflicting events or non-linked events at the same time. Basically, this means that if I'm sending transactions to my mum and Majay is sending a transaction to his mum, those two transactions will not be dealing with the same outputs or the same inputs, and they won't be going to the same addresses. So those two events can essentially have consensus operated on them in parallel. This is the first step to being able to have a massively parallelized network and being able to have the high scalability. Again, not too high risk. It essentially just splits out these blocks and makes them into single asynchronous events that then you can have a node working on multiple events simultaneously. And then the third version, RPN3, that's when it actually comes into when you start splitting the state information between shards, so that you have nodes that don't have all information in the network. So in RPN2, they still have all information, but are now able to parallelize. And then RPN3, you're now in a situation where state information is not shared by all nodes. And so each node essentially has to be able to pass state confirmation information between shards so that they can stitch these together so that you can get a fully you can get full synchronicity around events that maybe touch multiple shards with multiple nodes that don't necessarily have overlapping state information about those shards, and still be able to come to consensus. This is the hardest part, and this is essentially where most of the sort of R&D work is still being carried out. We have a pretty good idea about how to do all of these pieces, but as with all things in consensus theory and in computer science, when you get into sort of like these Byzantine systems where you have imperfect information from a node's point of view, you end up having to sort of deal with some really interesting edge cases that you just have to do a lot of research on. And this is again why we sort of working with UC Davis on things like this as well. So RPN1, relatively straightforward, relatively easy to deliver, relatively unlikely to end up with any consensus level issues, but could still end up with code level issues where there's some bad implementation or some bugs or things like that, which is why I talk about testing still being one of the unknowns around how long that might take and what that can cause in terms of delays. RPN2, again, relatively well defined. We understand how to state shard the particles. We understand how, relatively well how to parallelize events. And then RPN3, you start to really get into the complexities of splitting up state information between multiple nodes on lots of shards that aren't necessarily all overlapping. That's when it gets really difficult. Is Cerberus proven to be secure? What are UC Davies thinking of this? Yes. The short answer to that is yes. The long answer to that is it depends which version of the network you're talking about. So RPN1, absolutely. RPN2, yes. RPN3, we are still in the phase of defining all components of it. So when you prove, like this is a very technical question, and I don't know if you want to go this deep, but to prove a consensus mechanism is to secure, you have to do something called a formal proof. And a formal proof is completely different from the process by which you validate it to yourself. So like a lot of what you do when you validate something is you'll build either a simulation model of it, where you'll go, these are the behaviors that I want to simulate, and then you simulate the bad behaviors in the system, and you run the simulation basically sort of akin to a Monte Carlo, if anyone's familiar with that, but it's like a statistical model where you're just going, these are all the different ways in which I want to move all of these different settings in the system to see whether or not the system survives. That's fine, and it's a really good way of testing things, but it's not a formal proof of security. When you formally prove something, it means that you describe mathematically the way the system functions, and then you develop a proof, which is normally a It's very difficult to prove something is secure, but it's easier to prove, it's difficult to prove a negative, but you can prove a positive. So you can say, oh, it is secure under these assumptions and in these forms, and because it is secure in these assumptions and these forms, then it is secure as a system. We can use a number of existing proofs to how the single thread Cerberus works. So single thread Cerberus looks somewhat akin to Paxos and Hot Stuff, but the multi-thread Cerberus, especially with regards to basically stitching together all of the different shards, that's where things like leader selection and not being able to bias leader selection, or at least not being able to stall leader selection, is a really important proof to be able to get to, and that's a bit more complicated. So RPN1, yes. RPN2, high degree of certainty. RPN3, like from a can we code it and make it work point of view, yes. From a have we got a mathematical proof that says this is definitely not going to blow up under sort of some extreme scenarios? No, we don't have that yet. And so UC Davis has already been working with us now for, I think, 3 months, and all credit to them, they've really been putting the time in. So we have a weekly call with them, and it's with Professor Mosadogi, and then like a number of his team, and all of his team from the get-go have just been getting straight into the meat of it, like really asking the difficult questions, challenging Josh, Dan, Florian, Martin, Matt, and the rest of the team who are sort of like working on this on a regular basis. And they're really excited about it. They're really excited about publishing a couple of academic papers with us. It's sort of like what we did has very much run in line with what they were already researching. And when we came along, we were like, this is how we're applying these sort of like fundamental theories that you're already researching. They were sort of super excited to be working with us to begin with. So that's proven already to be a very productive relationship. And so you're going to see some more coming out about that. Next thing that's going to come out is UC Davis itself is going to be making a statement, and then we'll probably be publishing our first sort of academic reviews of this in the next few months, aiming to get our first like formal proof out before the ERC20 comes out. But again, that's not a certainty. That really depends on how quickly these sort of last little fiddly bits get wrapped up.